today, inshallah, but I hope somebody can start recording. Okay, great. We discussed the transient stability or developing the swing equation in multi-machine power system, pre-fault, during fault, and post-fault conditions. We discussed the detailed procedure in steps, how to start until you end up with the swing equations for each machine. And then by numerical integration, you can apply any methods that we have discussed earlier in order to solve the swing equations and judge whether the system would be stable after the disturbance or not. In all the discussion so far, if we assume that the line is pure reactance, so we assume that in the power P12 from bus 1 to bus 2 equal to V1 V2 over X12 sine delta 12. So this is of course this pure sinusoidal will be distorted if we add here a resistance. If we have a resistance in the line, so we have here like another term, and this angle will be shifted minus theta or minus phi, and this sine becomes cosine, and this is the angle of the admittance. We discussed all this in details in multi-machine. Now let us start with this equation, V12 equal to V1 V2 over X12 sine delta 12. Looking at this equation, what are the limiting factors for the power transfer V12? Depends on what? What are the factors that affect the power transfer? What do you think? Based on this equation, Ramadan?
It's the equivalent reactance.
Equivalent reactance, this is a limiting factor. Yes. What else? Hussein, Khalid, Abdulaziz?
The power angle also is a limiting factor.
الباور انجل ولا الروتر الباور انجل دلتا يمين
Delta, yes.
دلتا difference, yes. Delta 1 minus delta 2 will affect the power. What else? عمر تاو ولا طايو سلمان؟
V to determine our voltages.
Voltages.
The point voltage V1 V2.
Yes, and voltages also is a limiting factors. If you increase the voltage, then you can transfer more power. Voltage will increase here. If you reduce the reactance, you can transfer more power. If you increase the phase angle or the phase shift or the power angle difference, if delta increases, this sign will increase, and also you increase the power transfer. So here we have three limiting factors. If we can play with these three factors, then we can make our power transfer flexible. And this is what we have done here in FACTS devices. FACTS is a flexible AC transmission system. Flexible AC transmission system. FACTS. Why it is flexible? And these devices can play with the reactance, can play with the voltage, can play with the angle difference. So we can access all these three limiting factors for power transfer, so we can make our transmission system more flexible. So we have some types of FACTS devices that affect the transfer reactance. Some FACTS devices can play with the voltage. Some other type of FACTS devices can play with the angle between these 2 points. So with these FACTS devices, with these flexible AC transmission system devices or technology, we can make the power transfer flexible. So this is what we will discuss today, inshallah. Omar, do you have any question, Omar? Omar?
No, doctor, I don't
Okay.
know. I raised lower my hand. I don't know. It's coming up again.
Okay. Right. So let us see what we have. Okay, let us put it in presentation mode. So we will see the 3 types of FACTS devices, and each type will play with a certain factor that we have discussed just now. So we have a thyristor controlled phase shifter. So this will affect the angle delta 1. This is the phase shifter. So it plays with the phase or power angle. Thyristor controlled series capacitor. So this will play with X12. It can modulate X12. And static VAR compensator, which is shunt compensation, and this can play with the voltage. So these basic FACTS devices that can affect one of those. طبعا this is we call it generally, this is the first generation of FACTS devices. And we have second generation. We have some devices that can access reactance, voltage, and angle. I mean, we have different, but let us see the basic concept here, and then we can, if we have time, we can discuss about the second generation. What is the difference between first and second generation of FACTS devices? So these are the 3 FACTS devices that we will see, and also we will see how these devices will affect the power flow and how to modulate the power flow using such device. And what would be the power angle if we have phase shifter, if we have series capacitor, thyristor controlled series capacitor, and if we have a static VAR compensator. What is the power angle? Is it still be equal to V1, V2 over X12 sine delta 12, and this is the shape of B12, is delta 12. Let us see what is the impact of having one of these devices in the system, and what is the impact on the shape of the sinusoidal waveform that we have here. Okay, great. So let us start with the thyristor controlled phase shifter, which affect the angle difference between the 2 points where the power is transferred. The basic function of the phase shifter is to provide means to control the power flow in a transmission line. This control depends on the phase angles. This can be accomplished by modifying the voltage phase angle. Phase angle it has nothing to do with the voltage, but we change the phase angle by inserting a variable quadrature voltage in series with the transmission line. So in order to make a phase shift, and you have here, this is the line, this is 1 and 2, and you have here a transformer. This is a phase shifting transformer, a device where you can have 1 with the angle phi. So this is the turns ratio of this transformer. This transformer makes only phase shift, which is phi. The voltage magnitudes are almost the same, but this angle of the primary side, which is 1, if we consider it 0, then we have the voltage here 1 with angle phi. Or if this is theta, so this would be theta plus phi. So we have some phase shift between the primary and secondary. So in this case, we have delta 1 here, and we have delta 2 here. Now, delta 1, not delta 1 minus delta 2 in this case, but you have here an angle phi. So it is delta 1 minus delta 2 plus minus phi. So this is the phase shift between these 2 angles here. And this phi could be positive, could be negative. This is why we have plus minus phi. So the phase of the output voltage can be varied relative to that of the input voltage. As we mentioned, if we have here theta, so this becomes a theta plus phi, or delta 1 plus delta 1 plus phi. From delta 1 to delta 1 plus phi. So we have here delta 1 plus phi minus delta 2. So the input voltage by simply, okay, so the phase of the output voltage can be varied relative to that of the input voltage by simply varying the magnitude of the series quadrature voltage. And here, I don't know whether we have, yes, we have the phase, we have the structure or the phasor diagram in the next slide. So we'll discuss it in details. The structure of a thyristor controlled phase shifter and its phasor diagram are shown below. So this is the schematic diagram of thyristor controlled phase shifter. What you have here, you have the primary voltage. This is a transformer, phase shifting transformer. This is phase shifting transformer. You have here series transformer. This is series transformer. You have here shunt transformer, and you reduce here the voltage, and then you rectify it. You have a rectifier here, so you have a DC link there, and then you have an inverter. So this inverter will have a voltage here with lower magnitude, for example, 10% of the primary voltage or something like this. You can control it, definitely you can control it up to up to 10% of the, and then you inject this voltage here. So you have here voltage, comes from the inverter here, and this voltage will be transferred to the, you have it here V, and you have V prime, for example, and this is V, or delta V, let us say, delta V. So this is delta V prime, this is the primary voltage, and this is the secondary voltage of this transformer. So the voltage here is V, the voltage here is V, and the voltage here is V prime. So V prime now equal to V plus delta V. And if you control the magnitude of this delta V, then you can control almost this delta V will be injected quadrature to this voltage. So the phasor diagram is given here. So this is V, and this is delta V, and this is V prime. Delta V is very small compared to V, like 10%, 5%, up to 10% of V. So this is why V prime as a magnitude approximately equal to V. Approximately equal to V. Okay? So, but the angle now of V prime is shifted by angle phi. And this angle phi depends on this voltage, if it is 10% or 1% or 5%. So you can have different angle. You can control this angle by controlling the magnitude of delta V. If you control magnitude of delta V, you control this angle, and even you can make this angle, if this is the positive angle, you can make it also negative angle by having delta V in opposite direction like this. And this can be easily done through this switching mechanism here. So you can have phi, typical value of phi is in between minus 15 degree to plus 15 degree. So you can make a phase shift, and using this thyristor control the phase shifter by around 15 degrees. Okay. Any question?
Yes, Doctor.
I have a question.
Yes, please.
This switching mechanism, wouldn't it introduce some harmonics in the system or noise?
Yes, of course, definitely. Yes, we have. Since we have, switching or inverter or so, we definitely have harmonics here. But of course, you can, eliminate the harmonics using like filters. You can have here also some, instead of having six valves or 6 switches, you can use more switches. You can use multi-level inverter. You can use, of course, IGBT. This is the symbol of thyristor, but you can go to an advanced devices like IGBT or MOSFET. You have several advancement here. So these such IGBT using pulse width modulation or inversion, this can eliminate a lot of harmonics, especially low order harmonics. And in this case, you can have low size filters here to eliminate the harmonics if exist. And you can do, yes, of course, you are right. We have some harmonics since we have some switching here, but these harmonics can be eliminated by filters or by using some of the modern inverters that we have. Depends on pulse width modulation. So in this case, we can eliminate a lot of low order harmonics, which is very common here. Okay, Abdulaziz.
Okay, thank you. Yes.
Any other question?
Excuse me, Doctor. Doctor, here we have 2 transformers, TR1 and TR2. So both of them are the phase shifter function.
لا الphase shifter comes from the direction of this voltage with respect to V. And once you have here a DC, you kill all the phase shifting that we have. We have here DC voltage, so there is no phase shift. يعني حتى لو في phase shift هنا لو ده Y delta transformer and we have a phase shift here or there, after rectification, then you have a DC. So no, we cannot say or we cannot talk about the phase shift here. So we kill the phase shift here by having this rectification. The phase shift comes from the injection of voltage which is perpendicular to this voltage. And we can have this 90 degrees here between this voltage and V. So in this case, we can have, phase shift plus minus phi minimum and phi maximum. So is that okay, Horani?
Yes, it's okay, Doctor. Doctor, one more point. What do you mean by quadrature?
Perpendicular to V. And if this angle has an angle delta or theta, so this delta V will be theta plus 90. And the phase shift or phase angle between V and the delta V is 90 degrees.
Okay, this is what you mean by quadrature. Okay.
Yes,
Clear.
this is what we mean by quadrature. The angle here is 90 degrees between delta V and V. طيب, who else? Omar?
Yes, doctor. I'm thinking of something. What happens if the terminals of the inverter, the output from the inverters, are not connected the way it is connected? For example, if line 1 or phase A, if I may call it, is now swapped to phase B, I mean, when they are at the point of injection to the transmission line, does that affect the shifting?
You mean if we have this transformer, this primary is swapped,
Yes.
for example, to another.
Yes.
Yeah, of course. طبعا, of course. But you need the voltage of this phase and the voltage of this phase to be 90 degrees. Okay, we need 90 degrees. We don't need any angle. Of course, you can control this voltage. And later, if you go, for example, to the second generation of FEX devices, we have some new technology in power electronic that can give us this delta V in this locus. So this delta V can be 360 degrees, 360 degrees with any value. So you can control this delta V. The angle, you can inject delta V at any angle. But this is in the second generation of FEX devices. We have, of course, what we call the unified power flow controller, UPFC, and we have also synchronous series static synchronous series compensator. Static synchronous series compensator. So this one is similar to, this is actually similar to the this type, TCBSC, thyristor controlled phase shifter, and also thyristor controlled series capacitor. So this one can, have the same function as both. طبعا of course second generation is is more versatile and also has some other advantage in terms of the structure and the size of the equipment. As we will see later, we have some capacitors and inductors. So in this second generation, we don't need the big size of inductors and capacitors. So there are some advantages of this. But anyway, the idea is the same. Here for static synchronous series compensator, we have more flexibility, and we have this delta V. It is not only a quadrature to V, but we can play with the angle of this delta V, so we can have, the voltage could be added directly. We can have any angle. You can have some more flexibility. Okay, Omar. Ayub, well, do you have any other question, Ayub?
Doctor, sorry, doctor, here we installed this device in series. So also, so the X12 also increased. So, the angle increased, but also we increased the X12. I think this is one drawback.
لا طبعا الإكس here is very small. This is the series transformer. الإكس is almost zero here. And the X of this transformer, of this winding, for example, is almost zero.
Okay, clear, doctor. Okay.
Reactance, we are not talking about reactance. So the major function of this is to play with the angle here, phi. So we introduce a phase shift between V and V prime. So it is not now delta 1, 2, but delta 1, 2 plus phi, and this phi could be positive or negative. So this is what we have now. Okay? So you are controlling now the phase angle or the power angle difference between 1 and 2. So you can play with the power transfer. So this is the first type of the FACS device. Let us see another type, which is thyristor controlled series capacitor. So we have here a series capacitor. You have here XC, and you have here like controlling. You are playing with this XL here with these thyristors or gate turn off transistors. So you have here firing angle control. So with this firing angle control, you can control the reactance of this part. So for example, if these are off completely, so this L is is out of the circuit, so you have XC. If you introduce XL, so you reduce the XC, and so you can control the total reactance here. Total reactance, X total, can be controlled by switching these thyristors. So this is the line. This is the line here, and you have this device connected series to the line. Here you have XC, so you can control the transfer reactance. So the basic function of this series capacitor is to provide means to control the power transfer between areas and by modifying the net series impedance. So this line has a reactance X line, and this X line is connected series with the capacitor here, or control the capacitor. And this X can be controlled by switching of this XL, So at the end, you can control X1, 2. If this is bus 1 and this is bus 2, and you connect here this device series with the line, so eventually you can control the net impedance. So the structure of a fixed capacitor, this is fixed capacitor, controlled reactor. So you have constant capacitors here, and this reactor can be controlled by this thyristor. So you have this type. You can have fixed capacitor thyristor controlled reactor. Okay. So this is one of the structure that you can have. Yeah. Is shown in the figure below. By controlling the firing angle of this thyristor, you can control the amount of XL or the duration of XL to be in the circuit, and this will be reflected in the net XC, and eventually this line has a variable reactance now. Okay, the static VAR compensator, where we can adjust the voltage. This is the structure of the static VAR compensator. This is the connected shunt. The static VAR compensator is a shunt device. Unlike the thyristor controlled series capacitor, or this is the series. This is the series compensation or series device, or we can say series compensation. And you do compensation through series, and also for the TCVCC, this is also series compensation. Okay. So for the static VAR compensator, you have, again, this is another one of the structure. You have fixed capacitor and thyristor controlled reactor. So this is a fixed capacitor, thyristor controlled reactor. By controlling the switching or the firing angle of the thyristors here, you can control the compensation comes from XL, and you have compensation comes from XC. So the net compensation or net reactive power goes here will be adjusted. You can have plus minus, for example, 100 megavolt ampere reactive megavar. So you can inject either 100 megavar or plus or minus. Of course, this can be controlled. You can have 50, you can have 30 by controlling the firing angle of the thyristor. So static VAR compensator have been initially employed to regulate the voltage at the midpoint of the long transmission line. Usually for voltage compensation, you install the static VAR compensator at the midpoint of the line, and دي تعتبر يعني the weakest point in terms of the voltage like this way. So if you enhance it here, this would be great. Regulate the voltage and improve the power factor and increase the transmission capacity by controlling the voltage, enhancing the transient stability, as you will see later on. Of course, طبعا يعني usually these devices like static VAR compensator, mainly the primal objective or primal function of the static VAR compensator is for voltage regulation and shunt compensation of the reactive power compensation, power factor, and the voltage regulation. But what we wanted to say here in this part of the, in this lecture, is to say if we have such devices in our system, can we utilize these devices also to enhance the system stability as a secondary objective? And the primary objective is the voltage regulation and the power transfer. Yani for this one, the primary objective is the voltage regulation. For TCSC, thyristor controlled series capacitor, the primary objective is the power transfer. We need to enhance the power transfer. Our question now is, if we have such devices, can we use it? Can we control it in order to improve the transient stability of the system? So this is the objective here. So yes, we can use static var compensator to enhance transient stability, and with this we will see it at the end of the class, inshallah. How the static var compensator affects the power angle characteristic. So the basic configuration of the static var compensator of fixed capacitor and thyristor controlled reactor type is shown below. And let us see how these devices can modulate the power flow. How B12 is affected by the thyristor controlled phase shifter or series capacitor or static var compensator. Without fixed devices, the real power flow in the transmission line, this is the transmission line that you have here V with angle delta I, and this is the second bus, Vj with angle delta J, and the reactance here is as such. So you can easily write in the B12 or Bij equal to Vi Vj Xij. So this is the power without any compensation, without fixed devices. This is the without facts. We need now to see if we have phase shifter, if we have series capacitor, if we have a static var compensator. So how this power will be affected. Okay, this is the voltage magnitude and angle, and this is delta Ij, delta I minus delta J. Okay, so this is without any compensation. The real power flow through a transmission line with thyristor controlled phase shifter can be described as follows. This is the main system that we have, and this is the phase shifter. The phase shifter here, magnitude of voltage is 1, primary, secondary, but there is a phase shift of phi here. So how much of the power transfer will have this phase shifter here. So this is the power transfer, Vi Vj Xij, sine delta J minus phi or plus phi, it doesn't matter. And the phi could be positive, could be negative. Of course, طبعا you can see here, if this is in primary or in secondary. So if this phi in the secondary, you may have delta phi here, plus phi. But anyway, this is phi, could be positive, negative, doesn't matter here. Of course, you can easily derive it. The voltage here, and you can say in the voltage here, V2, let us, or V prime, مثلا, V over V prime, you can say in the VI with angle delta I over V prime equal to this turns ratio 1 with angle phi over 1. So you can have here V prime equal to VI with angle delta I minus phi. So this phi will be up, so it becomes minus phi. So this is V prime here, okay? So minus delta J, it becomes delta Ij minus phi as we have it here. So you can, by transformation ratio, you can get this angle, whether it is positive phi or minus phi. Definitely, if this angle phi is here, so this will be 1 over 1 with angle phi. So angle phi will be multiplied by delta I here, so you can have plus phi. Anyway, this is not a big issue. Hence, the real power flow can be regulated by controlling the angle phi. You can control the angle phi plus minus 15 degrees, so you can control the power flow by controlling the angle. Any question?
Yeah, Doctor, I just want to ask regarding the power of some FACT device to increase the power transmission capability or power transmission capacity. I want to ask how far can this be done in such a way that if I have 50 megawatts, assuming I have a 50 megawatt generator, and maybe what I want is 100. Can I say, okay, I will just get generations of 50 megawatt, and then I will use FACT device to do the remaining 50? Or can I say that, okay, I will only generate 30 and I will use FACT device for 70? So what is the limit within which we can apply FACT device?
لا يعني this is the generator and this is a transmission line, right? So you assume the generator is have 50 megawatt or what?
Yes.
Okay, this is 50 megawatt. So what you want to do now?
Yes. What I am saying now is that with application of a FACT device like static VAR compensator, for example, we can obtain, it is possible for us to get something like 55 or 60 megawatts at the receiving end. Is this correct?
No, that's not correct.
Okay.
Actually,
so why do
these devices are not generating power. These devices are not generating power. If you have here 50 megawatt, you have here 50 megawatt with losses. Of course, assume that this line is lossless. So what you have here is 50 megawatt.
Oh, so they don't even.
Of course, they are not contributing to the real power. They are not generating the real power. Now here the problem is, Omar.
No.
The problem is in some cases you have a generation here, but due to stability limitation, you cannot transfer this 50 to the far end.
Okay.
Did you get the point?
Yes.
This is the limitation. The limitation like you have generation capacity, but due to stability limit, you cannot, you have here, for example, this is the power transfer. This power transfer, Bmax, right?
Yes.
B12. This is delta. The Bmax equal what?
15.
The Bmax in general over 1x12, right?
Okay, yes. Yes.
So maybe this x12, due to this long transmission line, you have very high x here. Let us say x equal to, for example, 0.8 or 0.6, for example.
Okay.
If this x equal to 0.6,
you have Bmax equals 5/3. That's 1.67.
لا خلينا مثلا نقول بلاش 0.6، خليها 1.5 مثلا، or 1.2 مثلا. الامبيدنس. اوكي اور 2 يعني خليها 2 مثلا، يعني بي ماكس equal to 1 over x12 which is 2. So this is 0.5 per unit.
Yeah.
So if this is the per unit, if this is the rated power 50 megawatt,
Okay.
this is the 1 per unit. You cannot transfer this 1 per unit through this long transmission line. The maximum that you can transfer is 0.5. And the maximum that you can transfer is 25 megawatt only.
Only, yes.
This is the stability limit. Here the rule of the fax devices. Fax devices can allow you to transfer more power. You can transfer the 50 megawatt, but the fax devices are not generating power. They are facilitating the power transfer. This is the problem. And usually you have, for example, here in Saudi Arabia, long transmission line between eastern area. You have here eastern area, eastern operating area. You have central operating area. You have western operating area, and you have southern operating area. So this is long transmission lines, okay? And then long transmission line, what limits the power is the stability limit. يعني we have long transmission line and we have short transmission line. What governs the short transmission line, what governs the power transfer, or the limiting factor of the power transfer for short transmission line is the thermal stability. There is no issue about about stability. It's a thermal limit. So let us say thermal limit. So in short transmission line, what governs the power transfer is the thermal limit of the conductor. You don't need to exceed the current or current capability or current carrying capability of the conductors. So this is the limiting factor. Okay?
Yes.
But for long transmission line, what limiting the power transfer is the stability. Stability limit, as we have it here. Okay?
Yes.
So you can, يعني الconductor can carry more power, but due to stability limit, you are not bumping or you are not transferring through the line their current carrying capability. So you can have, for long transmission line, the stability limit comes before the thermal limit. And then for short transmission line, the thermal limit comes before the stability limit. And in short transmission line, this X will be like 0.1. So you have like 10 per unit you can transfer in stability, without hitting the stability. But the limiting here is a thermal limit. So in conclusion, to make it short, fax devices are not generating power. They are facilitating of power transfer. It helps the power system operator to utilize the existing capability of the network without adding new transmission lines or so. So here, for this long transmission line, if its reactance equal to 2, so that means this is the stability limit here, you cannot exceed 0.5 per unit. And if this is a 1 per unit, this is rated, so you cannot exceed 25 gigawatt through this transmission line. And of course, if the line is longer and longer, this will be lower and lower. Is it clear?
Doctor, thank you.
Okay. So
Doctor, excuse me, Doctor.
yes, please.
Yes, I have a question related to the previous slide. Now here, we speak about the limit of the transmitted power, but I have another question. Now we have, for example, x12 equal 2. So up to what limit we could reduce or compensate this x12? So can we, for example, add a capacitance with 2 also, so that we can have 2 minus 2, which is 0, for example? We have superconductor. Up to what limit we can compensate the existing reactance?
طبعا of course this will lead us to another problem. Compensation here, if you have a capacitor here, if you install a capacitor and this becomes minus J2, so that means the total, our net reactance will be 0. So theoretically you have infinite power that you can transfer. But this is, of course, in real life, you cannot do this. You have to study, you have to carry out another study, Hussein. This study is called subsynchronous resonance. You have to study this subsynchronous resonance, SSR. This phenomena or this problem happened in US in 1968 or 69. There was a series compensated transmission line, and you have here a generation plant. And it happens that the shaft of this generation plant with the shaft of the turbine, this shaft is damaged or was damaged. And they don't know what is the reason for this. So they reinstall it, and in the second year, 1970, it happened again. And the shaft is very, very huge. The shaft is not, you can imagine the forces on the shaft that destroy a shaft with 50,000 ton, for example. 50,000 ton, this could be the mass. What is this? And you can have the mass of the shaft is 50,000 ton. So although this is the very huge, but it happened twice, and they start thinking about the problem, and then they formulate this problem, which is called subsynchronous resonance, which happens with the series compensated lines. You may have a resonance between the electrical part of the system of having inductance and capacitance, and also with the mechanical part of the system. This shaft can be several masses. High turbine shaft, medium turbine shaft, the shaft of the high pressure turbine, shaft of the section of the intermediate pressure turbine, low pressure turbine, generator, exciter. All these have masses, And these masses, of course, will connected here like with the springs, like a mechanical system. And the shaft is not one part. Shaft is several parts as such. So, and this system also has a resonance frequency. So if this frequency, or natural frequency, if this natural frequency coincide with the electrical natural frequency, then we have huge forces on the mechanical in the shaft of the generator, and it will be destroyed. To avoid this, you have to carry out for the series compensation line. It is not just arbitrarily you can put any compensation. You have to carry out this study and you have to limit. But the typical value is plus minus 50. The minus is not recommended. We don't want to add another reactor here, so you can have a capacitor with 50% compensation. And this is what we can do. We can say, typically the compensation is 50% of the transmission line reactance. So if this is 2, so what we can do is -1. If this is the reactance of the line, so we can add a capacitor with half of this. So we can double. If we add half of the impedance, so we can double the power transfer. Usually, even here in eastern area and so in the central area, and also there are a series compensation here and a series compensation here, and this is not thyristor controlled but a switched capacitor. This is a switched capacitor. So you can control even the this compensation to 10%, 20%, 30%. You can have here, but what we have here in Saudi Arabia is a switched capacitor. It is not series. It's not thyristor controlled, or there is no other control than switching capacitors. But it will, of course, the switched capacitor, it will also help in achieving the, increasing the power transfer. You have here a capacitor at the end, and this capacitor will reduce the reactance, the net reactance of the line, and you can, send more power from eastern to central. So is it clear, ya Hussein?
Yes, Doctor, it's clear.
Omar, do you have a question, Omar, or you forget your hand?
No.
Okay. The real power through the transmission line also, or here the for series compensation, you can have this the reactance of the line, and you multiply it by factor, and this K represents the compensation level. Compensation level of the series capacitor. This could be, for example, 0.5. So you have 0.5 or 50% compensation comes from the capacitor. So you have this power. So the ratio between X of the capacitor over X of the line, and in this case you can have the thyristor controlled series capacitor here, and you can, of course, by controlling the firing angle, alpha is the firing angle here, the firing angle, طبعا XL is a function of the firing angle, as if you still remember the structure of this series capacitor. I should put it there also in order to avoid having it here. So this XL is a function of the firing angle here, and XC is parallel to it. And you can find the total reactance XC with XL in parallel, and XL is a function of the firing angle, and you have XC, so XC XL over XC plus XL summation طبعا, and you see you have this positive and this is negative, so this is XC. So this is the net reactance of the series capacitor. This is the net reactance of the series capacitor. So XL of alpha firing angle. طبعا of course if you go back to the sinusoidal waveform and the angle alpha, and you see you will end up with the XL of alpha equal to this value. So this is XL of the series capacitor, and then you can have alpha here, so you can control this value, and if you control this value, you can control the capacitor value that is injected here. So where alpha is the thyristor firing angle, means that the real power flow can be regulated by controlling the compensation level K. Okay. So a transmission line with SVC installed at the middle, the real power flow through a transmission line can be described as such. So you can have if you have here, this is VI and this is VJ, and you have here a middle line or midpoint of the line, so we have VM here. So you can write the power transfer through this. You have a capacitor here, and this is the SVC here. So the power here equal to this reactance Xij over 2 and the reactance here Xij over 2, لأنك أنت you install this at the midpoint of the line. So the power here equal to VI VM over Xij over 2 sine the angle delta I and delta M. So this is the becomes 2 times VI VM over Xij sine delta IM. Delta IM equal to delta I minus delta M. Normally, delta IM equal to delta Ij over 2. Usually, we have the angle here is half of the angle difference here, and the VM approximately equal to VJ. يعني the voltage difference is almost around 1 per unit. All voltages for the angle difference, voltage difference is not that much, and B equal to VI. The power flow can be written as VM approximately equal to VJ. We can replace VM by VJ, and you have delta IM is approximately delta Ij over 2. So we remove this delta IM by delta Ij over 2 approximately, and this is replaced VM. So this is the power transfer. As you can see here, you can see how the static power compensator affect the power now. So, for example, if I say at what angle this B becomes maximum power, at which angle? يعني احنا عارفين in regular cases ال B max
90 degrees
at 90 degrees, right?
Yes.
احنا عارفين ان ال B max at delta Ij equal to 90 degrees. But here, if we have SVC, you can see here in the B max occur at delta Ig equal to 180 degrees. If delta Ij equal to 180, so this sign becomes 1. So the maximum power will be transferred if delta ij equal to 180 degrees. And the maximum power here is double the maximum power here. Here, if this is Bm, this is 2B M. This is 2B max. So the power curve is completely different in case of these FACS devices, as we'll see here. So the equivalent susceptance of the static var compensator, again, you have the structure. If you still remember the structure of the static var compensator, you have fixed capacitor and you have a reactor here with the thyristors. You have it here. So this is XC and this is XL, and you have here the angle alpha of the firing angle. So you can write in the B, the susceptance equal to 1 over the impedance, 1 over XC, plus or minus the susceptance of the inductor. And you have 1 over XL. And BL is 1 over XL, but this is function of alpha, and you can have alpha, BL of alpha equal to this. You can have at any firing angle, you can have how much the effective value of the inductance here. So you can have this case. In normal operation conditions, VI, or normal operating conditions, VI, VG are around 1 per unit, assuming Xij equal to 1. The effect of the different compensation schemes of the real power flows is shown in figure below. So you can have this figure which combines all type of compensation that we have. If no compensation, this is the solid line. This is if no compensation. If we have series compensation, layer B equal to V1 V2 over X12 times 1 minus K sine delta 1 2. So this is the series compensation with the thyristor controlled series capacitor. So K is the compensation level. So if it is 40%, 50%, whatever, then you can have the same power. Maximum occurs at 90 degrees, but the Bmax is scaled up. So this is for series compensation. This curve for series compensation, same sinusoidal, but of course you can have higher Bmaximum here. For shunt compensation, as we just pointed out, and the maximum occurs at 180 degrees. The maximum occurs at 2 pi. Sorry, at pi. Maximum occurs at pi. Maximum here occurs at 90 degrees. 90 degrees. There, this is in radian, but here this is in 90 degrees, and this is at pi, 180 degrees. This is for static var compensator, and the maximum is double. Maximum is double of this, and if this is 1, the maximum here is 2 for static var compensator or SVC. Okay, so this is a B here equal to 2V1 V2 over X12 sine delta 1 2 over 2. So this is for static var compensator. For phase shifter, you are extending the maximum. You can control the angle phi, and you can reshape the power curve as such. So you can shift the maximum if you control phi, so you can keep the maximum value as equal to 1 per unit for plus minus 15 degrees you can play with. So you reshape the sinusoidal. It is no longer sinusoidal, but you can have some flat here where you can control the firing angle. So in general, the FACS devices reshape the bar angle curve, as you can see here. And I would like to ask you now, how this affects the stability of the system. يعني احنا we say انه الFACS devices can be used for stability enhancement. How can we relate the FACS devices effect to the stability? Can anybody tell us what is the relation now, or how can the FACS device improve the system stability? Yes, please, Hussein.
Increasing the critical clearing angle.
Okay. وبالتالي increasing the critical clearing time. طب هي ليه؟ يعني why? Why it increases the critical clearing angle? يعني خلينا
give us more flexible in the stability of the system. We will not lose the synchronism so fast with any small or sub-transient or transient events which may affect the stability.
Okay, you are right. But we can say, no, if we have such devices here, the deceleration area, which gives you the stability margin, will increase. And for example, instead of, if you have, this is B mechanical here. This is B mechanical. Assume that you have a three-phase fault. You are working, for example, here, if this is the capacitor. So you have this B0, and then you switch. So if you have the original, curve, you can see how much the deceleration area that you have compared to if we have a series capacitor. So you can see how much the deceleration area, all this is a deceleration area. All this area is a deceleration area compared to this area only. So the stability margin is increased a lot. For example, for SVC, if you have a three-phase fault, you are working here, then and the fault is cleared, you can see how much the deceleration area that you have. All this is the deceleration area compared to only this part. If you don't have SVC. Again, for phase shifter, this is the original deceleration area that you have, but now you have this deceleration area. And you add this part as well. This becomes also a deceleration area. So in conclusion, these FACS devices extend the stability margin, enhance the stability margin by increasing the deceleration area. Of course, as a consequence, the critical clearing angle, critical clearing time will increase. So you can improve the system stability accordingly. Do you have another question, Hussein?
No, thank you.
Any other question? Any question?
What about the unified power control? Power flow control. UPFC.
UPFC. Okay. UPFC is the second generation of FACS devices, unified power flow controller. This combines both series plus shunt compensation. So it looks like as series compensation, you have TCSC or triple SC, static synchronous series compensator. And you have shunt. Shunt is a static VAR compensator. And you have also STATCOM. This is the second generation. This is the second generation of FACS devices. Static, compensator. You have it STATCOM, which is similar to SVC here. Okay, triple SC is similar to. The unified power flow control do both functions here. So you can inject. You have shunt compensation and series compensation for unified power flow controller. This unified power flow controller. So you can inject here a reactive power, and you can inject here a voltage with angle with 360 degrees. So you can have series compensation here. And the beauty of the second generation, and if you look at the yes, here you can see here we have inductor and you have a capacitor here. For the second generation, we don't have such passive elements. We have what we call the voltage source converter, IGBT, and by switching, we can emulate the capacitor or the inductor here, and we can control the. This is the just a brief introduction to second generation of the. And of course, a lot of details we can have for second generation, but the idea is the same. We need to extend the power stability and by modulating the power transfer. So this is the idea. Okay, Omar, I know time is over. We take more
Thank
time.
You,
but this is the case. Do you have any question? If you have any question, please stay and ask. Otherwise, you can leave.
Yes, Doctor.
Abu Bakr, go ahead.
Doctor, for the series compensation, can the capacitor affect the angle?
لا يعني angle, what do you mean by angle? يعني you have here this one. Of course, this is the capacitor. يعني affect the angle. يعني you are not interested in the voltage and the current through the capacitor. We are interested in the net impedance of this line. So the net impedance is Xij minus XCC. Okay. So this is the effect of the capacitor here. Of course, the voltage across and the current through, but this is not an issue. And the current here leading the voltage by 90 degrees. But this is not an issue here. Abu Bakr. This is a question?
Okay, doctor. Thank you.
Okay. If you have any other question, please. Otherwise, you can leave.